when raced in the American Solar Challenge. Unfortunately, again, that was a learning experience, as I conducted a NASA mistake from many years ago, if you remember the Mars landing. When converting from metric to standard and standard to metric, did the conversion wrong, and my axles were a little bit weak, and we broke an axle. It happens. I also have a master's degree in systems engineering, which is what I'll be talking about today from the Naval Postgraduate School. I also have one from the National University of Singapore, which most of you are probably not familiar with, but in the Asian world, that's kind of the equivalent to MIT for them. So, and could I focus me, please? Okay, so being a military guy, I tend to like some military quotes. Well, actually, I'm going to do that. So what are information systems? We stole this definition from Wikipedia. An information system is any organized system for collection, organization, storage, and communication of information. More specifically, it's the study of contemporary networks and people and organizations that are used to collect, filter, process, create, and distribute information. Stolen from Wikipedia. So that's a lot of words to basically say how to use information. So why are we talking about this topic? To build a solar car and to race a solar car is a series of decisions. You have to make decisions on your design. How many wheels are you going to have? What motor? What cells? How long is your car going to be? All those decisions that go into building an effective solar car. Once you've built the car, you're going to race the car. You're going to have to make decisions on what speed you're going to run, who's going to drive the car. All those decisions, making good decisions, is going to allow you to win the race. And that's why we're all here. But in order to make those decisions, you have to have a basis for how you're making decisions. So, on there. It's really embarrassing when the AV guy loses his microphone. Okay, so all those decisions, and good information leads to good decision making. So you're going to hear me, that's kind of the takeaway from this presentation. You're going to hear me say that a lot this time. Good information leads to good decision making. Okay, so ubiquitous sports analogy. I am not a sports fan, so I will apologize. I could talk about cricket and rugby. American football is not, but that's what most people understand, so that's what we're going to go with. So we have the situation. You have 4th and inches. What do you want to do? Coach, okay. So.
Go for it.
Okay, well, that's one. But, okay, so what information would be helpful for you in making that decision? Would you like to know where the ball is? It's on the 30-yard line. It makes a difference. You're probably not going to go if it's on your 2-yard line. Your team has a 50% conversion rate. Okay, that might be helpful. It might not. It's good to know. Your field goal is 70%. And we're going to actually stop and talk about that one for a second. So, yeah, we'll talk about it later, actually. The opposing team has not stopped a conversion all year. Yeah, that's a kind of important piece of information. So both of those pieces of information are not something that's obvious. You can't look at the other team and know that they haven't stopped a conversion all year. So in order to do that, you had to collect data, you had to analyze that data, and then you had to present it so that you could make a decision. And that's what we're talking about today in information systems. That's the same thing with a field goal kicker. And it's not an intrinsic probability of field goal kicker. You can't look at William over there and say, he can kick a football, and 70% of the time it's going to go in. You're going to have to watch how he performs. You're going to have to record his performance. You're going to analyze it and then present it. And we use percentages a lot as a very simple way that you can wrap your head around quickly. It's much easier to say he can kick 70% than he kicked 35 out of 172 kicks. Both of those, well, actually those two, my math doesn't add up there, but you could say the same information, but one of them is a lot easier to interpret. So, and that's it. I think everyone's going to go for it today, so as I said, good information leads to good decision making. Okay, and my quote, as I said, I'm a military officer, so I like military quotes. Sun Tzu, a Chinese military general from about 300 BC, said, if you know the enemy and you know yourself, you need not fear the result of 100 battles. If you know yourself but not the enemy, for every victory gained, you will also suffer defeat. And if you know neither the enemy nor yourself, you will succumb in every battle. So we're going to talk about how you know yourself and how you know your enemy. Okay, so know your enemy. information systems. How many miles do you think it's going to take to win the 2019 Solar Car Challenge? What? Well, that's a guess. Anyone else have a guess? 700, okay, that's a good guess. Any other ones? Okay, well, I'll go through So what we're going to do is first we're going to use an information system. First we're going to gather some information, then we're going to analyze it, and then we're going to see what we think. Okay, first we gather data, we analyze it, third we're going to display it, and we're going to talk about how we make decisions. So data. There are lots of data sources in this world. They're almost an infinite number. In our case, we're going to use something that's probably familiar to you, the Solar Car Challenge website. And we've got the results from every year that we've run the closed track event available on our website. So I went out and collected my data. I used another piece of software, which most of you are probably familiar with, called Excel. Wonderful Microsoft program to collect all the data. So you can see all of our years. Okay, so that's a beginning to analysis of it. We did some simple analysis of it. We got the minimum, the maximum, and the average number of laps. So 50, I think you're going to be right out. 700, pretty good. So that's a very basic analysis that took about 2 seconds to do, as you could say. We know 50 is too good, 700 is probably good. But then we plotted it. So as humans, we're really good about looking at visual data and plotting trends. So we can kind of make some quick assumptions on that. It looks like it's generally trending up. So we did some math. Excel has a wonderful feature that allows you to fit a trend line, so definitely going up, and we were able to find a formula. And so then we projected out, and so if that trend continues, it's going to be 840 miles to win in 2019. But as I said earlier, we're pretty good at looking at trends visually. That's why we like to plot things. And we notice that there's some outliers in there that we might not like. Oh yeah, I forgot my decision slide. So now that we've analyzed that information, how do we use it? So we took that 840 miles, we looked at the number of hours that are available, and found out that it takes 27 miles an hour for the 8 hours a day that we race in order to achieve 840 miles. So what does that mean? Well, that means if you're gearing your car to do 50 miles an hour, you might be over-designing it. If your car has a max speed of 20 miles an hour, you're probably not going to be able to get there. So that's how you use that information. The example of how you use that information to make good decisions. And so I said visually I didn't particularly like that information. So we chopped off some of the first years where there were some outliers, obviously it's increasing, and fit another line, which looks much flatter. And so this one, if we ignore the first 2 cross-country events, we come out with 710 miles. So good guess at 700. Or 22 miles an hour. So that's, again, if you're thinking about trying to design a car that can do 50 miles an hour, that's great. But that might be a little bit overkill. It might be taxing your resources unnecessarily. Okay. So know yourself. So that was knowing your enemy. You now know your competition. Now knowing yourself. So by nature of solar car racing, we're very limited by the amount of energy we have. You're limited by what you bring with you in your batteries and what the sun can produce for you. How you use that energy is incredibly important. So I have worked with a lot of teams over the years, both high school and college teams. I was an advisor, had a mentor from MIT. I'm still an advisor to the Georgia Tech Solar Car team. And so I have lots of data from lots of different teams. I have seen the same car drive the same course within 20 minutes of each other and use vastly different amounts of energy. It's the order of 30% different amount of energy. So how do you know that? Well, just like the field goal kicker, you can't look at a driver and know that I'm a very good driver and Michael there is not a very good driver. It's not intrinsic. You have to go out and collect some data. You have to analyze that data. You have to see it. So, how do you know yourself? Well, the most important part of knowing yourself is driving. There is absolutely no replacement for testing your car. And there's a belief, both here and at the college race, that the car that shows up with the most miles on it is the car that wins. Why? Because they know their car. They know what's going to break. They know that hopefully nothing. They know they're reliable, but they also know how to drive it, and they know how to be efficient. You may show up with the best car in the world. You may have the perfect design, but if one, it's not reliable, and two, you don't know how to operate it at its maximum efficiency, it doesn't do you any good. And so in order to collect that information, telemetry, it's probably, in my opinion, I am a little biased because this is what I do for a living, probably the most important part of a car. And there'll be a whole presentation on that after lunch. Okay, and so telemetry is a system. So the first thing in any system, you have to decide what you're interested in. There are an infinite number of variables that you could possibly look in. You have to identify sensors and methods to collect that information, just like the website that we talked about earlier. Pick a system to record it, process it, and then display it so that you can make good decisions with it. So 2 years ago when I gave this presentation the first time, we sat down for about 5 minutes and came up with a list of variables that might be important to you in the solar car challenge world. And this is a huge list, and this is by no means exhaustive. This was 5 minutes of me sitting down with William and talking. You know, things like the temperature, your location, your speed, the battery current, voltage, all important. Things that you might not think of as obvious, like the time of sunrise and the time of sunset, are pieces of information that are valuable to you as you plan your day, plan your charging and your driving strategy. I mean, even things like if you're trying to model your car, things like the driver weight, your corner weights. You might want to know your motor controller temperature. Motor controllers tend to become less efficient as they get hot. So there are all kinds of things that you could possibly use, but everything has a cost. In order to measure all these, it would be insanely expensive and require lots of effort and system. So you probably want to pare it down to what's important to you. Okay. And so once you've picked the ones that are important to you, you have to figure out how you're going to measure it. And so we have a collection of sensors here, some of them which are probably familiar to you. We've got a current shunt, the little blue one. There is a Hall effect sensor. It's another way to measure current. We've got a potentiometer if you wanted to measure, for example, how hard or how softly your driver was pressing the gas pedal, the brake pedal, or what the travel of your suspension was doing. You've got a GPS antenna. You've got a little temperature sensor, position sensor that you would use for like GPS or use for like a bicycle for speed, and the ever-popular potentiometer. So once you're looking at sensors, it's important in vocabulary when you're thinking about sensors. You have the range, the sensitivity, the resolution, the precision, and the accuracy of your sensors. So the range is the interval of which will provide readings within the design parameter of the sensor, which is a lot of words. So every sensor you have has a range associated with it, from 0 to 12 volts, from 0 to 100 amps, or 100 to 200 amps. If you're working outside of those ranges, your sensor is not likely to be effective. It may still provide you a reading, but it's likely not going to provide you a reading that has value. Sensitivity is an absolute quantity. It's the smallest absolute amount of change that can be detected in a measurement. So this is how small it is. So for example, on your multimeter, how many digits out you can read? Is it 12.1235 volts, or is it 12.1? And this can be really important or it can not be important. Older lithium-ion batteries, 3.14 volts is about the safe charging voltage. 3.16, and you run the risk of starting a fire. Kind of important thing to know. But if your voltage meter only has a resolution of tenths, you may not know that it's 3.1 or 3.2. Same thing. Same thing goes with temperature, same thing goes with speed. All these have sensitivity on the sensors. Resolution is the degree in which a change can theoretically be detected. So this goes into a whole, very closely related to sensitivity, commonly confused, and for all intents and purposes the same, but it has to do with the entire system. Accuracy, and the amount of uncertainty. So if we go back to our voltage sensor, if it says it's 3.14 volts, is it really 3.14 volts, or it might be 3.16? Generally, those are expressed as a percentage of the entire range. And So the more accurate and the more precise your sensors are, generally the more expensive they are. Sometimes it's important, sometimes it's not. Oops. Okay, so accuracy versus precision. Kind of similar concepts, but not exactly the same. So the easiest way to show it is a bullseye. So is this accuracy, or do you think this is accurate or precise? I'm going to go with none of the above. That is not low accuracy, low precision. How about this one? Yep. Low accuracy, high precision. They're all about the same. So in this situation, if you were high precision but low accuracy, you can adjust for this. If you know what your offsets are, you can change them. So this is actually not a bad situation to be in, so long as you know where you are. Also, why testing is important. Yep. High accuracy, low precision. This can be an annoying one because sometimes it's very perfect and sometimes it's off a little bit. And then we have the ideal. I'm sure we've gotten to high accuracy, high precision. Okay, so we'll talk about data loggers. So once you have all these sensors, you're collecting all this data, you have to do something with it. You need to store it in some method. So using that, you're going to use a data logger. And there are basically two flavors of them available. They're commercial systems and they're DIY systems. Commercial systems are by far the better option. However, they tend to be very, very, very expensive. They also tend to be set into different systems, so you get tied into their system. So you're tied to their sensors, their ideas, and their cost structure, which is the one thing. So we have had teams that have had a lot of luck. One of our teams has had a 3M system, and we had another had a $25,000 telemetry system that was donated to them. I just forgot the name of the company that did it. But that doesn't fit into everyone's budget, and not everyone can have one donated like that. There's also a lot of options to DIY. We have an entire lecture on that after lunch, but the DIY benefits are they tend to be cheaper. You can customize it for exactly what you want, and you can go out and mix and match parts to make it work instead of being tied to one company's ideas. And when thinking about data loggers, you need to think about whether it's analog, digital, the communications protocols. And this goes back to sensors, whether you can talk to things you want to, the number of channels, and how you want to get the information to the users. Okay, so once you've collected your data and stored it, you have to process it so you can analyze it. So this is the results of the 2015 Solar Car Challenge. This is actual data from the race for one of the teams. So this is pretty clear to everyone exactly what was happening? Yeah, clearly. Yeah, so we processed it, just a little bit of formatting. It's a little clearer, kind of can see better what the lines of our data looks like. So a little bit more formatting. And now it's a lot clearer what's going on. First, we know what team. This was the scoring for a walnut. We know the time that the information was recorded. We know their location, that they were required trailering at this snapshot. We know their judge, which Christian Amadeus. We know their speed and their heading. So this is all the information that we needed to analyze to score the race. And this was all done in Excel, so just a little bit of formatting can make things much more approachable. But sometimes you need to go a little bit more on formatting. Sometimes just a nice spreadsheet is an easy way to look at data. But sometimes there are other ways to do it. Numbers are great, but there are a lot of other things you can do. We've got some pictures of some charts. As I talked about at the beginning, we're really good at analyzing histories and trends visually. So charts allow you to go back in time and have that quick reference. Hey, we're slowing down, or we're going faster, or we're drawing more current. Really quick to analyze that. Things like the speedometer in the middle are just a quick indication. Once you have the scale, you may not actually care so much about the number, but you know that there's not a change. You're very consistent. It's not jumping around like a number. And then we have just some other waterfalls. Stoplights. Sometimes you don't actually care what the number is. It's irrelevant to you that your motor controller is 105 degrees. But it's really important, it might be really important to you if it gets to 120. So you'd have a big red, we call them idiot lights. That may be super important. But the actual data behind it is not as important to you. So you get light. And we have a couple of dashboards here that show them. Like the check engine light would be a perfect example. I don't have a check engine. Actually, I do have a check engine light on there, or a tire pressure gauge that we have right there. You might not actually care exactly what the pressure is, but you do care a lot that it's low. So those are a good indication for lights. And just some of the battery gauge is a good variety of different ways that you can. This one you have more precision. This one, you don't actually care about the exact percentage, but it gives you an idea where you are for quickly. Okay, and this is what I would do. This is my disclaimer. There are no right answers. This is my answer. Actually, we're not going to go too far into that this time. If there are right answers, this was not. And not in the Respect Solar Car Challenge. So what I'm personally interested in, and this is based on my experience, are the currents are the most important thing that you can deal with. How much current is basically equivalent to how much gas you're using. In batteries, you measure the capacity by amp hours. And so in order to find, that is how full your tank is. You have 100 amp hours, 200 amp hours, whatever. So in order to know how much you've used, you need to know how many amps you're using. If you know how many amps you're using and how much time you have used it, you know your amp hours. So my top 4 items are the currents. Your battery, so you know the current coming out, you know the current going in. I measure the auxiliary for the same reason. It may not be important to everyone. The array voltage and the battery voltage, because those tell you about the health of your system. You should have a good idea what your array is putting out. If your array is not putting out the voltage that you expect it to, you might have a problem. Same thing with battery voltage. Especially if you're using or if you're using lead acid batteries, the voltage of your batteries is a very good indication of your battery health and how much storage you have in your batteries. If you're using lithium-ion batteries, they have a nice flat curve, but then they have a drop. If you get into that drop, you have reached the end of their charge. Knowing that you're in that drop is very important, so push it. I measure the throttle position. This goes back into knowing your drivers. Being able to look back and seeing why driver 1 was different than driver 2. The indication is generally how fast they're hitting the pedals, both the gas and the brake pedal. So generally you want to be very smooth as you're driving a car. You want to slowly and gradually apply the throttle to get to the speed you want to be, and then you want to stay there. You don't want to just slam the pedal down, get to where you're going, and then rapidly let off, slow down, and go back and forth. That's about the least efficient way to do it. So if by measuring the throttle position and the brake position, you can say that. And you can go back and have a chart and show your drivers, like, you're really jumpy on the throttle. Person B is really smooth. This is how you should drive. It's good for providing feedback. And finally, speed, because all these things, how you relate to the speed, your current as it relates to the speed is important. That's how you know your car. If you have a certain speed, you're drawing 100 amps. If you go up a mile an hour, you might be drawing 200 amps. You may not, there are needs in the curve of your current usage. You might want to make sure you're below 1 or above 1 to be efficient. Some of the more advanced things, the weather. A lot of people don't think of that as an information system knowing their car. But we have a really good example of that from last year's cross-country race. The last day of the race was a really miserable day. Was that 2 years ago? It was so miserable that we were considering calling off the race. They were predicting rain, sleet, snow, all the horrible things. Not really, it's summer. But it was overcast, it was bad. So we had a team that was supported by their local meteorologist. They went back and analyzed the data, used computer models to analyze data, and reached back, and found out that the weather was supposed to pass. So we gave teams the option of trailing forward. So some teams trailed forward and tried to get ahead of the weather, looking at it. We had one team that stayed back at the beginning of the race and sat at the start line for 4 hours and waited for the weather. Well, their model was correct, and the weather passed, and they were able to drive the entire day. Whereas the teams that tried to get ahead of the weather lost the first half of the day. And that was the difference. The first and second place teams were the two teams of interest. The second place team trailered ahead and tried to get a hold of the weather, so they lost part of their race day to trailering. The first place team stayed at the start line. If those teams had reversed their actions, it would have changed the outcome of the race. So that's an example of why this information is important. And then I like the weight and the road profile because this goes back to you can model your car. You can very simple, you've taken physics, force equals mass times acceleration. You can figure out how much energy your car should be using. And then you can go find out if you're meeting your expectations or not. And then you can make projections for what's going to happen in the future as you're driving down the road. Okay, the sensors I tend to like Hall effect sensors, basically because they're non-contact sensors for measuring current. You don't have to have a shunt. You don't have to put them in line. You clamp it on around the outside of your power line, and you measure your current. Voltage are simplest sensor, but you need a voltage divider for a lot of these systems. Most data acquisition systems are not meant to take 96 or 120 volts or whatever your car system was, so you need to break that down. Thankfully, it's very easy to do. It involves two resistors. You can take just about any input voltage and put it into any system. Potentiometers for the pedal sensor, and then I like GPS for speed. A lot of people use bicycle magnet type sensors. I find GPS is much more reliable. And that's all I have for this one. Have any questions? Okay.
Would you suggest using, I know there's a way.
Unfortunately, they're having a corporate reorganization this year, and PyTop is not with us. So the actual PyTop system is not necessarily something I'd recommend. However, the Raspberry Pi, which is at the heart of a PyTop, I'd highly recommend. And if you happen to have a PyTop board from last year, those are outstanding boards, and they did a great job designing them for us.
Thank you.
System of collecting data from your car. It's the physical hardware, the data logger, the sensors of how you collect data.
And that will be covered in the 1:30 session. You'll get more information at 1:30. All right.
Okay. Solar Car Challenge, on the left, there's a thing for the workshop, and all the presentations will be, I think this one's actually already on there, but all the presentations will be on there by the end of today or tomorrow.
Thank you.